All right, so this is almost where we left off. We did actually we spent a lot of time doing change of variables, right? But this is almost where we left off in part one, right? One thing I'm adding is this initial boundary condition on the surface of the sphere. There's a minor change. This, I think in part one I did as n squared, I'm going to use m squared, right? So with this, we did a change of, this should be squared, this should be sine theta, cosine theta. All right, so with this equation, if I do x equals to cosine theta, change a variable, then that gives you that differentiating by theta is the same thing as dx d theta of differentiation by x. And because if you differentiate cosine, you get negative sine theta, like that. And then that means theta double prime, which is differentiating twice by theta, would be, you can rewrite this part as negative sine theta of theta differentiated by x. But then if you differentiate using the product rule, this part is differentiating negative sine theta gives you negative cosine theta, theta differentiated by x, and then differentiating this theta x by theta, well, this is same as that, so it's like negative sine theta multiplied by this negative sine theta and differentiation by x of theta x. So that's going to be same thing as sine squared of theta. This thing I'm going to write like this, theta x differentiate twice, and then this one would be minus, well, cosine theta is x, right? So I can write x is like that. And then sine squared theta is like 1 minus cosine squared, but cosine is x, so you get that, right? Yeah, I'm showing you this because I did something similar, but I realized this is faster. It's a slightly faster way of deriving this result. And you still have sine squared, which is 1 minus x squared. You can change these in a similar fashion as well. And if you divide by sine squared to everything, so that this is gone, we stopped where I said, well, let's use y of x as big theta of theta, because then I don't have to write differentiation by x. Because y prime means differentiation by x. So you get, what you get is 1 minus x squared y double prime. There's a negative x derivative by x coming from here, and there's another one somewhere here. So you get negative 2x y prime plus lambda minus m squared over 1 minus x squared y equals 0. And I explained that the solution of this equation, well, this equation has a name. This is called associated Legendre differential equation, and its solutions are called P ml of x. And what's L? Well, L, it turns out that the solution of these are usually non-physical because theta is from 0 to pi. 0 is the North Pole and pi is the South Pole. The values of x would be cosine 0 is 1, so 1 on the north pole and negative 1 on the south pole. So you're looking at functions defined from negative 1 to 1, but at negative 1 and 1, this vanishes, right? So that causes some singularities to appear in the solutions. And usually, for most lambda values, it's going to happen that one of the solutions will have a singularity at negative 1, the other solution will have singularity at positive 1, which is no good. Both are not physical. We throw them away. By the way, singularity means you have a vertical asymptote, so it's infinity. And you can't have that if you want a physical quantity, right? Your solution should be a finite number. So the only time that would have something that behaves nicely is when you have this lambda being equal to L times L plus 1, where L is, I said last time, positive integers, but L could also be 0 as well, okay? And also M has to be something in between L and negative L. Only when these two conditions are met, you would have solutions that are finite. And for M even, including 0, this will always be a polynomial. And of course, polynomials don't have any vertical asymptotes, right? M odd will have, it will look like something like a polynomial times some square root of 1 minus x squared multiplied somewhere, okay? Now, for the special case when m is 0, that equation is called Legendre equation. And if you recall, phi was C1 cosine m phi plus C2 sine m phi, right? That in the radial direction, this direction. And if m is 0, what does that mean? That means this is a constant, right? So what that means is if you solve Laplace equation where the boundary condition doesn't depend on phi, if it only depends on the latitude, you know what longitude and latitude is, right? On the Earth, longitude is like
north and south.
No, longitude is like, I think 0 is the Greenwich, and then how far east or west you go from there. Latitude is you have the equator, which is 0, and if it's north, you go up or down. That's slightly different because our system has 0 on the North Pole, so it's a bit different. But anyways, so it's the case where your boundary value function, if this doesn't depend on phi but only depend on the latitude, then your solution will only need m equals to 0 part, and the solutions can be written as Legendre equations where we drop the m. See, if m is 0, then we don't have to put m there, it's 0. So we just write PL of x, and there are formulas for this. The formulas are, let's see, this should be L factorial x squared minus, D L x squared minus 1t L, where D is differentiation by x. So you could just solve it, but you can also.
What is DL? DL is just ddx?
You differentiate ddx to the lth power, meaning that you differentiate L times. Yes.
And the denominator, is that 2 raised to the L times L factorial?
Yeah, 2 raised to the lth power.
L factorial.
And L factorial. Yeah. So that's that, and then and this formula is not the only way to write down this Legendre equation, but it's the most convenient way to write it. This has a name. This is called Rodriguez formula.
Have we calculated the formula before?
So I haven't shown you how to do this,
okay.
and
Does
if
no
we
one
have
do
time, I can show you why this is the solution. And then this one will look like the following. Will be yeah, it's 1 over 2 to the L factorial. You have L plus m factorial divided by L minus m factorial, and x squared minus 1 to the m divided by 2. Again, differentiate L times of, I thought I remembered this. I have to look it up. Yeah. L plus m, and then x squared plus minus 1 to the Lth power. That's also called Rodriguez formula. Okay, so I'm going to spend some time showing you how this one works later after this, but this one, once you see this, you can kind of believe that you can do something similar to get this one, because this already is quite complicated. So you can accept this one. And there's some other aspects of this. So this part is, the highest order is x to the 2Lth degree polynomial, right? And if you differentiate this L times, what do you get? You get degree L polynomial. Right? So for example, if this was 3, then this is a 6th order polynomial, but then you differentiate 3 times, so you get a cubic polynomial, right? Yeah. So P3 would be a cubic polynomial, P4 will be a quartic polynomial, P5 would be 5th order, 6th order, and
so just use the chain rule, and so we got.
Yeah, you just have to use the chain rule to differentiate sufficiently many times. And then another fact is that this crazy thing here is given because they choose a normalization where PL of 1 is equal to 1. So for any Legendre equation, if you give a Legendre polynomial, the value at 1 will be 1. And then I'll also explain. Okay. And I'll just throw in some facts, and then as we have more time, we'll prove these things. Okay. Another thing is that if you have the same m, and let's say you have j x p of kx, and if you integrate from -1 to 1 dx, this will be 0 if j and k are not the same. So, in other words, you get an orthogonality result. Okay? And then if they're equal, then you get something crazy. So I have to look it up. You get 2 over 2L plus 1, 2 over 2J plus 1, J plus M, J minus M, factorial, and that's it. Right. Okay. So that's what you get. And this is crucial for being able to represent any other function. So if you have any, see, now you have f theta phi, and x is really cosine of theta, right? So let's for a moment fix the phi, and think of f theta of some fixed value, phi 0, as g of x, where x is cosine theta, right? Because f has to be periodic from 0 to pi, is it? Oh yeah, it has to be, yeah. No, it doesn't. Well, it has to be defined from 0 to pi, which means x is defined from -1 to 1. So this is a function that's defined from -1 to 1. And what you want to do is you want to be able to expand this in terms of Pm j x and then some coefficient aj, right? J from 0 through infinity. Right? And what happens here is that see, this is degree m, because squared and m over 2. It has square root when m is odd, but it's something like that, right? So for at least for m odd, at least for m even, this is an order m polynomial, whereas this is order L minus m polynomial. So, right? No, we differentiate. So 2L minus L plus m. Yeah, right. So this is L minus m degree polynomial, and you have multiplied by an m degree polynomial, so you have degree L polynomial. So this is going to give you degree I need fixed m.
Is it degree L polynomial?
That will be a degree L polynomial. Yeah. At the end of the day, especially when m is even, it will be degree L polynomial. If m is odd, then odd over 2, that's like 1/2 power is there, so there's a square root, so it's not a polynomial. They still call it associated Legendre polynomial anyways, but it has some degree. And then, yeah, so if you want, so because of this condition that m has to be less than L, if you are hoping to represent it for a fixed m and different values of j, it has to start from m. And then to represent this as the other guy, you better have some kind of orthogonality result like before. So if you recall, when we were doing Fourier series and Fourier-Bessel series, what enabled us to figure out these coefficients? These kind of results, right? Yeah, because we multiplied this by this thing, both sides, and you integrate. Then most of these are 0 because of the orthogonality property. But there's some non-zero value here, so you can isolate one of the coefficients. So that's going to be important. Now, again, if we have time today, I can show you how this thing works only for m equals to 0, and it gets more crazy if m is non-zero. Okay? So hopefully we'll have time to see that. Okay, so there are actually two things that we figured out from here. One is that once you have that, the outcome is capital theta of theta is this y of x, where x is cosine, so you have to use this formula to get this thing. So it will be PML cosine theta. That's your, see, we're just looking for building blocks, so it should be really some constant times this, but we don't care. where m is between L and negative L, and then L is non-negative, well, L is equal to 0, 1, 2, 3, so on and so on. Yeah, there's so many things going on here, so it's hard to say them all. So I may forget some things, but here's another fact, that P of negative m this is like, the only difference is this just gets flipped. So if I multiply L minus m factorial over L plus m factorial, P L n. So something like this works. In other words, one is the multiple of the other, and which means these are not linearly independent. So you actually could say that, well, you're kind of listing too many building blocks here, because some of them are not linearly independent. So shouldn't you do m from 0 to L? Well, that's one choice, but we're still going to keep it this way because we're going to do a bit of change in the phi guy. Okay. I'll explain it a little later. Right? Okay, so that's one thing that we got from the associated Legendre differential equation, but we also got something as a bonus, that lambda should be L times L plus 1. Now why am I saying that? Well, that's because we still have the equation for R, right? So the equation for R was R squared R double prime plus 2R R prime minus lambda R, but because lambda, we figured out the only time we get physical solution is when you have L times L plus 1. It must be this one. And now we, seeing that this is a Euler-Cauchy equation, the solutions look like what R of R is. How does the solution of this look like? When you have 2R squared with two derivatives, 1 with one derivative, no R with no derivative. That's called
RK?
Huh? Yeah, that's called Euler-Cauchy, and then the solutions look like R to the kth power. Right? So if I plug this in here, well, first of all, differentiating once gives you k times R to the k minus 1. So R prime, if R is R to the k, then R prime is k times RK minus 1. If you differentiate yet another time, this will be k times k minus 1 times R to the k minus 2. So once I plug this in here and there, this is the equation that you get, and then minus L plus 1 R to the k equals to 0. And now you see that this times this is R to the k, this times this is R to the k, this is R to the k. So if I divide by R to the k, then I get k minus 1 plus 2 times k minus L plus 1 equal to 0. And you get k squared minus k plus 2k minus L plus 1 equal to 0. So this is like k squared plus k. Right? And then that factors as k plus L plus 1. Yeah. And then k minus L equal to 0. You can check that this plus this is what? L plus 1 plus negative L is 1, right? And if you do this times that, negative L times L plus 1 is exactly this. So we found two numbers that multiply to this and add to this. So that tells us that k must equal to negative L plus 1 and positive L. Which means that capital R must be a linear combination of C1 r to the negative L minus 1 plus C2 r to the Lth power. But we don't like one of the solutions. Which one?
First one.
Huh? The first one. Why is this bad?
So for singularity.
It's like 1 over r L plus 1, where L is non-negative, right? Yeah, non-negative. So it could be 0. But 0, 1, 2, 3. So this always has a singularity as 0. So this is not physical. It goes to infinity as r is sent to 0. If you plug in r equal to 0.001, you get a huge, huge number, which is not physical. So that tells us that the solution r must be r to the L. Okay. So that's good because we have the r, we have theta, we have the phi, and therefore we can write down the general solution now. U r theta phi must equal to this building block, this one, and then, oh, I should write this as a big sum, sorry. Big sum of r to the L p m L cosine theta, and there's actually C1, so I'll use A and B. So A m cosine m theta plus B m sine m theta. Right? But those coefficients can change with respect to L as well. So I'm going to put A L m, B L m. Okay. And then summation m goes from negative. Oh, for this one we should do m goes from 0 to L, and L goes from negative infinity to infinity. Okay? So that's how we should write it. And then to get these ALM and BLMs, we need to write down the integral by working out the two things. There's the cosine m theta, sine m theta, which requires the Fourier series in terms of, why did I put theta here? It should be phi. Cosine m phi and sine m phi for the Fourier series with respect to phi. And we also need to do series with respect to the Legendre polynomials, or associated Legendre polynomials. So we have to do all that work to get the ALM and BLM. But that's not how people write it. So let me work a little bit harder. So instead of cosine m phi or sine m phi, people use e to the I m phi. They use this instead. You know, there's e to the I m phi and e to the negative I m phi, right? There are two things. Those are the two linearly independent solutions for each value of m for the capital Phi, right? When you work out the Sturm-Liouville. But we don't use this. We use cosine and sine. Why do we do that again?
No complex one.
Because these are complex valued, right? So these are complex valued. That's why we don't use that. However, it's customary here to actually use this one instead of that. It makes the formula look simpler. That's one. Another is if you use this in the settings of quantum mechanics. So these things up here, when you try to solve the hydrogen atom with the Schrödinger equation, then the wave functions in quantum mechanics, they are actually complex values. So they don't really care if you have this. But even for real valued case, there's still ways to use this one, and that's called complex Fourier series. I don't think I'll have time to do it today, but next class I'll explain what that is. Okay? So instead of using it that way, we write it as summation L from negative infinity to infinity. See, you don't put m as 0 to L, but make it go from negative L to positive L. That way, even if you only write a single m, you both have the negative and the positive. Right? So it will be like C Lm r to the L PL m cosine theta e to the I m phi. So that's how people write it. And still, they actually use something further. They call something called the spherical harmonics. And these are defined as ml theta phi. And I'm just copying this straight from Wikipedia. I hope they didn't make a mistake. They rarely do. I think this is right. You have 2L plus 1 over 4 pi L minus n factorial L plus n factorial, and then PL cosine theta, then e to the I n p. So in other words, they take this part with some coefficient. Now this coefficient is really the square root of this, the size of this. So I explained earlier that if you have fx times gx, that's like a dot product between two functions, right? In our case, if I have a function on theta phi and another function on theta phi, and if we integrate this over the sphere, where this is the surface of the sphere, this will act like an inner product, or the dot product that we know of, right? So what's like the I forgot how do you say it? What's like the norm given by the dot product? So do you know this thing? What's v dot v? This is same as, if you dot any vector against itself, it's same as norm v squared, right? And this norm of the first times norm of the second times the cosine of the angle between, but the angle between is 0, so that's what you have. So if you take this function right here, and put it in here, then you get, see, this integral, if you recall, what was the integral? It was the integral that I wrote down was m plus n factorial over L minus n factorial with the 2 over 2L plus 1, right? Well, I used J a moment ago, but that was the value of the thing squared, right? So this is the value that you get if you do this dotted with this self squared. That was one of the values I wrote down. But because to get the norm, you have to take the square root, so you have to take this quantity in the square root. And how about this one? This one, it's an integral of, well, if you, that one, yeah. So this is an integral over the circle as 2 pi. So that gives you 2 pi as its norm squared. So you take the square root. You multiply these two so that 2 pi times 2 gives you 4 pi. you take the reciprocal of this quantity, that you get exactly this one. So you get this normalizing thing. And why do we do that? Because if you normalize, then you get this nice thing that says if I have y n k theta phi, and you integrate over the sphere, and I'm actually hiding something that's a bit complicated here, then this is 1 only when m is n and L is k, and 0 otherwise. So that gives you a very easy way to figure out the CLM, because all you have to do is, oh, there's actually one thing I forgot here. There's a bar there. I wish I didn't have to explain what that is. That's complex conjugate, and if you want to define inner products or dot product for complex vector spaces, I think some of you haven't, most of you haven't seen complex vector spaces, but if you want all the nice properties of the dot product, especially the one that I wrote down, v dot v equals to norm v squared.
What's it when a plus bi is the number then?
Yeah, so a plus bi, if you take the complex conjugate, you get a minus bi. That's called a complex conjugate. But if you multiply these two, you get a squared plus b squared, right?
Right.
So because of this, it gives you this nice property that we want. So there's this bar thingy, and this one is called Hermitian inner product. Yeah. So you get this much better, cleaned up version of the orthogonality relation, so that you don't have to. I mean, this basically takes care of all the ugly things that happened on the other interval. Okay, and this will give you the entire. So this will give you the basis for all the possible L2 functions on the sphere. So any function, as long as this f theta phi is given as an L2 function, you can write this as this sum, right? Because after all, what is u a theta phi? That plugs in a into r, right? So you end up with an equation here, CLM times a to the L is the unknown constant that you have to figure out. And this orthogonality relation can allow you to figure out exactly what that coefficient is. Right? So that means we solved it. I wish I could give you a concrete example with something in here, but that's like too much. So, this orthogonality relation can tell you what these unknowns are, if this is given explicitly.
Which part is the base? Which part is the base?
These form a basis for L2 functions on the sphere. So if you want, I can actually write down the formula for CLM. CLM will be 1 over a to the L, because when you plug in a to the L has to be divided in order to get it. You integrate over the surface of the sphere of, well, I actually have to write this as a, so there's something, do you know in spherical coordinates that dv equals to r sine theta d r d theta d phi? Have you seen this? Well, in multivariable calculus, theta and phi is interchanged, so this is the one that you saw. You've seen this, right? So in our case, it's this one, but because it's on the surface, r is a fixed value, and we're thinking of this as an integral over the unit sphere r equals to 1. Not a, it should be on 1. So it's really d omega on this curved sphere. It's sine theta, no dr, it's just this. Okay? And theta goes from -0 to pi, and phi goes from -pi to +pi, and you multiply f theta phi with the y and ml conjugate theta phi sine theta d theta d phi. No, sine theta d phi d theta. Because theta goes from 0 to pi. If I switch these two, I can switch these two. So that's the formula. So if you're given any arbitrary function here, we can calculate this whether by hand, which is usually impossible, or numerically. Okay, if you do that, you get all these coefficients, and then you can plug them in here, and you get the general solution. So that's the full solution. Now, just one more comment on this. The name spherical harmonics comes from the fact that if you solve the wave equation over the surface of the sphere, then you end up with UTT equals to C squared times nabla U theta of phi. But this is like Laplace-Beltrami operator, the one that's like the Laplacian on the surface. And if you do the separation of variables, then you end up with this being some eigenvalues, and you end up solving the eigenvalue problem of the Laplace-Beltrami operator, which is exactly the same as this one. So if you solve the wave equation on the surface of the sphere, you run into these spherical harmonics again. Okay. So this comes up in many places. You can do acoustics on when you have a gigantic ball and you hit it and you get a sound from it, and you want to know what kind of modes there are, you use this. Also, when you're trying to do geodesy, which is like you have geographical data and you want to know the harmonics of it, you use this. Or even in cosmology, if you have, let's say, cosmic microwave background, and you want to know like the independent components of that signal that you get, you use this. Yeah. And in many cases, they have slightly different values here for their own purpose. See, this one is kind of only for quantum mechanics, because they use it to make something called raising and lowering operators work well with this. But in many other places, they don't have it, and all that. Okay. But that's called spherical harmonics, and they appear when you try to solve the Laplace equation in the on the ball.
The field we solve is the surface contains the space in the sphere, right?
What did you say?
The whole ball contains the inner space. Or
Yeah. So we're solving the Laplace equation where the boundary condition is given, and you want to know what happens inside.
Okay.
So that's why R can be any value from A to 0. And theta is from 0 to pi, and phi from -pi to pi.